Resume. There we go. All right. So I'm gonna, I mean, Frenzel, we covered the Frenzel PowerPoint lecture pretty much and the way he applies it. And in the next chapter, that's where he starts getting into the nonlinear applications, if you will. So like I said, well, we're gonna jump around with Malvino supporting us a little bit here. And in chapter 18, go back one here, is linear op-amp circuit applications. So we're kind of looking at linear op, the inverting or non-inverting amplifier and building upon that. And in this case, I mean, we start off with looking at the DC amplifier, inverting and non-inverting, and then we'll look at the AC amplifier, and then a couple of application circuits like the instrumentation one, the summing, a weighted, something they have a current booster, if you will, and even a simple single power supply circuit. Because again, these things are they're relatively easy to use and set up, and we require minimum components, so they become cheap. So if we do need like different voltages, like on a PCB board or something like that, we could very easily use an op-amp circuit, and it would have, if we get the right kind, of course, I mean, it would have enough where it would drive a current out as well. So we wouldn't be having to worry about that. Sometimes with some of these devices, especially like the transistor drivers, you have to be careful that you don't overdrive, otherwise you'll be pulling too much current, and then you'll short these things out. They can only handle so much. And then you got the heat ratio as well, where the op-amp one, well, we'll get into that here. So let's look at a basic inverting DC amplifier here. And got two little golden rules on the side there. The one on the right, it's just a juggling around of the gain formula, right? Where V out over V in is equal to, and this is inverting, so it would be a minus R2 over R1, okay? The feedback resistor over the input resistor. And then on the left, we see a formula where it calls in what our total resistance would be. Now, remember that with op-amps, we always have our potential here is a virtual ground point, okay? So we always have a virtual ground, ideally infinite, right? So it would be an actual ground. Realistically, depending on the device, but a very high mega ohm range for this. And because of that, what will happen is these two guys will be in parallel and set the value of this to have a balanced circuit. And then this one is, we have a variable DC input. And then down here, remember that's our what we call our offset null, just to balance the amplifier. And remember again, the way to do that, we would just basically ground out this input, monitor our output, and then adjust the pot to basically swing that baseline right down to a nice smooth 0. And then your op-amp would be, your op-amp circuit would be tuned, okay? Oh, we juggle with it a little bit. This here. And plug in some, this is the non-inverting one, which very similar, right? We change around a couple of things, and we use the non-inverting formula here. And so instead of a minus RF over Ri, like an inverting one, we use a 1 plus R2 over R1. Okay, and again, virtual ground in between the 2 points sets us up for RB is equaling the parallel equivalent of R1 and R2 in parallel here, okay? And you got your offset null. Same deal. These, and this is a full pin out. That's why I kind of like the Malvino models, because he actually does show you, your whole full pin out. If you would count them up, you would get 7, and this is an 8-pin IC. So one of them is literally unused. If you look on the spec sheets, you'll find it. I mean, there might be a couple out there that have some strange deal with I think it's pin number 7, but in most cases that's an unused pin. It does literally nothing but take up space. No. All right. So take a look at an AC amplifier with these bad boys. So here we got a simple little circuit, right? We have an AC input with a source resistor and a coupling capacitor on the input. So what is that going to do for us? So on the swing of things, what that'll do is that by the value of that, we would, with our RC time constant, we would be setting up on our swing, right, the lower cutoff frequency. So what would our limit be? Our limit would be what we specify by the value of the capacitor. Look further in here and we see, so what's our formula that we would use? So the lower frequency, right, 2 pi RC, or in this case, you have your source resistor here, and then viewing from, what we call viewing from the driving source, right, is the input resistance of the next stage. So up to that point, right? And then we come up with our equivalent R value with the capacitor value we selected, and then we would find out what our lower frequency cutoff would be for this particular circuit, which would be this right here. So if our value is set, right, our lower cutoff would be at 10 hertz right here. And then we'll look in a minute and see what determines what our upper limit would be. And remember, these things have a really high overall gain, right? So our upper limit is set by the gain bandwidth of the circuit itself. So what we get on the output here. Oh, does that make sense? Is that and if we look at it, basically just plugging in a formula, time constant, right? 1 over 2 pi RC, and give our FSC in the lower range there, which would give us this. And these guys are simple that way. That's the cool thing about dealing with op amps compared to like transistor models and stuff like that. Everything we have set is just basically based on the components we have here. And then if you remember, when we looked at the transistor model of the differential amplifier, right? And the CM here is common mode. Just remember what that's standing for. And we have 2 inputs essentially to this guy. So essentially what will happen is both of these voltages will fight it out and see who's the winner, right? So if we take a formula, we use the inverting formula in this case, okay, because that's where we're tied into. Notice how on the non-inverting on this side we're grounded out at after R prime 2, we have an R prime 1. So yeah, this works very much like the transistor model. It's an easier thing to deal with. You have a less of a setup, if you will. Excuse me. And so instead of using like 2 opposing transistors, we essentially just use the 2 opposing, the inputs as opposing. And there's different ways we can play with these as well. And it's just using the rules of the op amp, that E plus equals and follows E minus. So the voltage established here will be the voltage established here, if that makes any sense. And so then we show a little formula for all varying values of R, okay, with the common mode. This would be our range, if you will. So we can't specify a dead center for this thing because it could be different inputs that we would be putting in here, but this would be our range value. And how we would look at it, where would our gain model be? Well, it would be greater than 2 times varying values of R over R, but less than 4 times that amount. And yeah, it'll be we'll get a lab where this will be a little more clear, have you work out some problems with it and play, and then you'll actually be able to see, well, what happens with the voltages as we adjust here. And that would be determining what your outputs would be. And like I said, just looking at applications for how we use op amps out there. So these would be some of the labs we're going to go into, and I'll have a lot more going into that. So we'll have different problems. We'll be setting up. This one will be a fun one to do, differential amplifier. And then we do another one. And remember, these are all linear applications. So this doesn't have like any crazy swings with it. It's fairly straightforward. The outputs are fairly straightforward, not subject to like radical change or anything like that. And we look at another one that coming up. It's the instrumentation amplifier. And this one is actually quite popular. And the reason being, you can, it's very easy, low components. If you see, these are all our bullet points, right? We have low noise, low thermal drift, low power consumption, low output impedance. And then what we have we get a really high gain of 10,000, a very high input impedance of 30, yep, that's giga ohms, okay? That's humongous. So it means we can handle quite a lot of current with this as well, right? We got a high common mode rejection ratio and 94 decibel swing, basically giving us our bandwidth, right? And a slew rate of 35 volts per microsecond. Remember in a graph how that all looks out for us. Basically, I mean, we get it. It's huge. So the instrumentation one kind of builds. If you look, the way we have this circuit tied in, right? We have basically two almost unity gain styles here because our inputs are literally without any resistant values, where we would have to plug in on the non-inverting side. We look at it down this way, where we have established a virtual ground point here. And what ends up happening is the way the circuit gets balanced out, your common mode AB is 1, right? So this is a unity gain circuit right here. And then that would feed into, and why would they do that? Well, the name itself, an instrumentation amplifier. So we're getting our voltages in, and if they had any degree of noise to them or anything like that, we would basically be using this whole beginning part here to reject any kind of noise or feedback or anything like that, and feeding in nice crystal signals into this guy. Okay, and he's the one that's actually going to be doing the work here. These guys are basically, really look at them as being like filters, because that's essentially what their job is that's why we have a gain of 1. So they're not amplifying anything, they're not changing anything, they're literally just reproducing our signals, right? And notice, because we have it on the non-inverting inputs, so we're not changing the phase of it or anything. So we're just really keeping these guys, they're basically signal filters, nice clean signals that'll go right into this over here. And then we look, now we got an AV of -1. So what does that mean? Again, you'll get the signal, but it'll be 180-degree change. Always look at that when we're looking at op amps. The minute we see our AV is -1, that means whatever our input is, we're literally going to flip that by a cycle, okay? So you'll get that 180-degree shift to make it a negative. And then we see our common mode gain here would be a ±2 over any changing values of R over R. Now, I don't want to get, because to be honest with you, that's a calculus formula, right? The minute we get into anything with delta in it, we have to start doing differentiation, and we are not going to do that, okay? Just suffice it to say that what he's trying to say is that any given values here, see how we just have R, 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 and R, okay? Any given value for that, this formula will work. And so and hence, being linear. If it was non-linear, we wouldn't be able to give it a dead set formula like that, right? Because then we would be saying, well, we got a certain range that we can do this and this through, but after that it changes, and after that it changes. Well, that becomes non-linear. But with linear, this formula would apply in any case. And plus or minus, meaning depending on the values here, it can swing either way, okay? But that's just a certain, like the formula for the overall circuit, if you will, is this one here. This guy here is your common mode here for the gain. This one here is the gain for this, and this one here would be for the output. So really, that's it. Boom, 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 and there's and there's all your formulas for it. Because common mode. Now remember what we're saying about that, right? We're looking at what the overall range is, or what our bandwidth would be for this guy. And we look at an actual real here's an AD620 monolithic, which means it's going to be one of the cans. It's going to be like have a steel enclosure. It's a type of material that the amplifier is made out of, right? So monolithic instrumentation amplifier. Very simple. You got an offset resistor there, right? 2 DC inputs. Pin 2 and 3 are your inputs here, and 6 is your output, and there you have it. So really what they have, and this you get actually, believe it or not, from the spec sheets overall, would be what your like gain formula would be. And so I don't know, it would just matter if you see here what my value of this is. So that would be considered like a gain resistor, if you will. Excuse me. So if you look, it just plugs in different values for RG in this case. So these are fairly standard. And then what our gain factor would be with that value of resistance, right? So if we wanted to gain 100, we would make this that, a gain of 75, and so on. And these would be my different applications of this circuit, if you will. Oh, guard driving. Now, what would you think that could possibly be? This is an interesting circuit. So notice that we have a shielded cable here, okay? And we got common mode inputs feeding out. But we got this guy coming back around. So what does this circuit do? Believe it or not, it protects against like ground bounce or like current spikes, that kind of thing. So if you ever wondered what kind of little circuit, you know, like your transient suppressors and whatnot, that kind of thing, how you would guard them. Huh? Oh, I thought I heard something.
Someone else needs to mute.
No. Oh, what do we got? Oh, am I getting that? I am getting that. Damn it. Supposed to be my the software is supposed to be apparently not working today. Anyway, let me turn my volume down here. There we go. But yeah, it's a simple circuit. And really all it is it prevents against any ground bounce, like transient current, that kind of thing. It would prevent any alterations in your signal, if you will. It's just a unique little simple circuit, cheap, easy. I don't know if we'll actually be doing a lab on this particular one. Maybe, I don't know. I doubt it. I would be more interested in like the instrumentation, and then this guy here. This one's another one from if you do like audio amplification and stuff like that. This one, the summing amplifier, where you had, and this can be a cascade. You don't have to just have like a 3-volt limit. There could be quite a stack going on here, if you will. You would just basically, you know, cascade your inputs down and have more resistance values added in for your varying inputs. And they sum it's like a sum of all going into this. So our input resistances, if you see here, R1 equals R2, so they have to all be what you call equal value, if you will. And then finding out, and again, our rules don't change, so we got a virtual ground point here. What would our value of this guy be? If you notice, R4 is equal to him in parallel with all of these, depending on how many you would have. So in this case, we have 3. So all 3 of those in parallel with him, and that would give us our value here. And our output, as you can see, hence the name summing, would be an additive of all of the voltage inputs that you would have with your overall feedback formula, right? The minus RF over RI. So in this case, we used the R1 as this all, they should all be equal value. Otherwise, you would get a little bit different circuit. And you'd have to do a lot more math involving like how would the impact of the varying resistors be with that. But yeah, it's a simple, widely used, has a lot of applications to it, but very easy to set up. And yeah, summing amplifier. So we can look, we have different voltages inputs here. So 100, 300, and 500, all equal value resistors here with a 10K feedback and equivalency of 625 ohm on R4. So just by plugging in this, you can get everybody down here in parallel, come out with a 625 on R4, then figuring out what our output voltage would be. We could see, you know, low level signal, right? 100 millivolts, 300, 500. And what we're getting out is an inverted 4.5 volts peak, right? So minus 4.5 volts peak would be seen on this guy. Because that's your load resistance. So when you look at the output, you would really want to look at the output here and not here, because this one's tied into the feedback loop. So you'd be dealing with the closed loop function at that point. So we'd be looking at it at this point if we were to go put a probe on there. And in this case, so you get the weighted amplifier, very similar, right, to the summing one. But if you look, yeah, see, this is what would happen if you had a varying resistance values. So this would be our formula that we would use, because these are not all equal. We would have to take each leg into account. So each one becomes its own little circuit, if you will. So overall, it's a minus because we're in the inverting input. So that mathematically we would look, okay, so what's my input? Well, that's this. We have the V3, V2, and V1. And with their corresponding equivalencies, right? So we always take it with the relationship to the closed loop with the feedback resistor here. So it would just be 1 for R1, 1 for R2, and 1 for R3. You plug out in all your math, and then you would get what your overall voltage output would be. So this would be, so if we just had different resistance values plugged in, right? Varying values of voltage, if you will, and what their like weight would be. So what is that? This is like a basic digital to analog converter. So this is your most significant bit, and this is least significant bit. And these, well, if you've done digital, really all this is powers, okay? So anything to the power of 0 is 1, 2 to the 1 is 2, 2 to the second is 4, 2 to the third is 8, and 2 to the fourth is 16, and so on and so on and so on, depending on how many bits we would have. So yeah, whenever you see a digital to analog converter, this is what you're doing. So you would have the corresponding, so if we had 8 bits, we would have to have 8 different inputs here, right? Starting, again, the most significant bit being the most weighted one, if you will, down to the least significant. And that would be your logic input going into and converting into an analog input. So again, just basic, we're using the inverting input. We would have to come up with our equivalency resistance here based on these resistant values with relationship to him being in parallel, okay? And then you come out with your overall voltage input, their weights, if you will. And by the cascade of values here, I mean, it just simply plugs down, boom, boom, and then you just come out, oh, well, each one is this. So then you would just have to go through, and if I'm dealing with like TTL logic, of course, right, those would all be like 5s or 0s depending, and then that would tell you what your voltage output would be correspondingly for digital to analog. Any questions on that? I mean, it seems, I mean, we'll do a little circuit with that. It won't, I don't know, it's not as, the most fun with this would be actually hooking it up to like a driver, like if we were to use, I don't know, like a JK flip-flop or something like that, right? Where we could actually vary the inputs to the flip-flop and have it, you know, kick something out and feed your amplifier circuit, if you will. But that's essentially what they would do. And in this case, it's what, he's just a little 4-bit D to A. So just imagine with like if you're dealing with a 64-bit, something like that, it can be done. The math would just be a pain in the butt because there would be so many inputs to deal with. But this day and age with the calculators and whatnot, it's not bad. Yeah, and then we look at what a little bit of transducers and how that comes into play. We're going to look at later on too is thyristors, which tie into this somewhat, kind of, sort of, and it's a little similar to like a transistor, but it's got one extra layer to it. When we get into it, you'll see it's a very strange device, but it's actually got a lot of applications out there that you would find running into as industrial techs. And transducers, I can promise you that in most walks in the electrician world, you will run into some applications where you're dealing with transducers. But we don't go into it much at this point. It's just like a brief mention to it that, yeah, we will be using these and what will we be using them for? And what do they use them for? Well, that is how we, he's just going back through like all the various uses linear wise, what you could do with these. So, I mean, you'd have to look at almost like Wheatstone style usage, right? And if we had a Wheatstone bridge set up with a transducer, it'd be one way we could measure quantities like non-electrical. Like if you're taking weights of something, you're trying to measure stress of something, you know, stress gauge or something like that. That could be a transducer where you'd be taking a mechanical signal, right, and turning it into something electrical, and then that would go in, and almost the vice versa, where we would have this analog signal coming in and being converted into a digital signal. But yeah, you'll run into, you know, various instrumentation uses different transducers, pressure measurements, all kinds of different things for that. But yeah, and then the good thing about these is you would want a really low noise, high gain amplifier. And what would that be, right? An op amp of some degree with a high impedance to it. So that way we could amplify the signal to a usable voltage level. Because usually, yeah, you get the transistor outputs are extremely small. They're somewhat of a pain to deal with because you can't, I mean, with you got your handheld meter, just trying to look at the straight output of a transducer can be a pain in the butt. But you would go and look at your amplifier output, and then you'd go, oh, okay, here's what our signals actually is. Then we get into something a little bit, current boosting, where op amps can give us a nice relative boost to our current, depending on the style that we use, right? So we can boost up our short circuit output current. Let's say we had like a low signal level or something like that, but we wanted to actually drive something with it. Well, we could have like a low amplifier in there giving us a very low current. You see, like the typical is less than 25 milliamps. But if we go and use one of the big heavy shielded ones, the steel ones, right? We can actually, if you see here, yeah, you can get 3 to 10 amps out of those things. And of course, you know, those are the ones that you'll see on like the giant heat sinks, because cranking out, you know, 10 amps from a device is quite a load. So we take a look at a little circuit with that. And you can see that we have a BJT hooked up to the feedback loop here. To the op amp. And what would and of course, because now we're dealing with transistor, we have to go back, oh, what's our beta of our DC again? And calculate what our final output load. I don't know, it might be interesting to go and take a look at this just because of the combination of the transistor and the op amp together. And these are kind of widely used out there for any kind of driver circuits. You would run into this kind of combination where, where you want to get like a high current output. You very typically would have this circuit. We might take a look at it, like a little review, have you guys juggle a couple of values and stuff like that and compare it to what you get on the simulator. And then on the same principle, but now you've got, instead of unidirectional, so just with the one NPN transistor there, now we go with a bidirectional, see, where you would get an NPN and a PNP. So that way you would get both alternations without the clipping. So you clip on a positive, right? So boom, boom, and then our reproduction would be the full output signal here. And that would be if we're really trying to drive, if we're looking for, instead of like a rectified signal, if you will, now we're getting a full boosted signal on the output. So we might play with current boosters a little bit in the lab. I haven't totally decided. I know for sure we will be doing the, the summing amplifiers. That's a very widely used one. We might take a look at the D to A weighteds. I doubt the instrumentation one as well. I'm sorry. I know, I'm flipping through here. One good thing about having a computer control. And we can even look a little bit at like a little single power supply, if you will, if you wanted to provide a given voltage. Very commonly used on PCBs. So you might have like different voltage requirements on the printed circuit board. So, and if you only had like one or two possible inputs, you could use these to provide you with different voltage levels if you needed to. That type of thing. It's a very simple circuit to do. You just have to figure out what your overall bandwidth is going to be, right? Our upper and our lower. And we can figure out our overall gain with the inverting signal, right? Notice how we have VCC tied in this leg as well. So he also is a coupling capacitor, because don't forget that E plus equals and follows E minus. So what you get here, you're going to get here. But we try to balance that out with this, and then essentially get an overall output. Would depend on what kind of signals we're looking for. I mean, this is a fairly simple, straightforward one. We're not doing too much in the way of of componentry or calculations, really. We just have to figure out what our cutoff frequencies are, what our range would be, if you will. So in this case, 3 different formulas for your frequencies of cutoff, and then your overall gain formula. And again, it's just an inverting. If you look at, really, if we cut away all the coupling capacitors, if you will, really it's just a simple inverting amplifier, just with a degree of input to it. And what could you expect to see in the output of something like this? Well, there's very typical, so inverted. And then with this guy, you would have a DC shift, right? But we don't want that. And that's his job would essentially be, right? Get rid of a DC blocker, if you will, and give us that same signal reproduction without the DC in it. So we might play with that in the lab. I haven't, and that would bring our, basically all the linear type circuits, all the main ones. I mean, you can go look through, and there's always going to be a lot of different ones that different engineers have built. But we'll go through. We'll have a non-inverting lab. I know we'll do one with the AC And then we want to jump into like the differential application and take a look at that compared to like it was when we did it with the transistors. And again, like I say, this one is a lot easier to deal with component wise. And then we'll probably play with the instrumentation one as well, just because again, it's very, very widely used. And even though this, you would be amazed at how many things this circuit actually is used in. Any kind of like shield protection and that kind of thing. These guys would be in your like cable plugins and stuff like that. You would, if you really were to investigate it, you would probably see this little simple circuit right in there. Transient suppressor, keeps noise out, blocks current spikes coming back on the line, screwing with our line. And yeah, we'll play with the summing amplifier for sure. Probably the weighted one just because of the digital analog thing. But I mean, really, once you get the whole summing thing down, it's very easy shift to go to the D to A, but it is an interesting thing to note. And now we have to deal with the bit orientation, if you will. Are you guys have all done like the powers and multiples of 2, right? Cascading up. I don't know how many bits that Bob's had to go through at this point, but so this isn't like new for everybody, I would hope.
Nope.
No.
Well, John's asking me if there's any due dates on these labs. Well, you know, I was doing the due date thing with them, but I'm telling you what, just because everybody's schedules and whatnot, asking for like extensions and stuff, I thought it would be easier if I could just go ahead and keep like open due dates on them. And again, but when I do this, and I know, you know, and some people, I'm out, you know, we all do it, we procrastinate. And yes, there will be, well, let me think. We do have a quiz I think we're gonna have to do. Hold on here. Let me stop that. Let's look.
Actually, I had a question about Lab 10.
If we look, I don't know if this, hopefully this follows us. Yeah, so we did chapter 37 homework, right? So now I need to, yeah, we got the quiz. Well, the one thing, I think for the homework, I'm not gonna assign one yet because that would be going into chapter 38, and I kind of wanted to, like I say, touch bases with the linear application. So I'm not going to assign a homework today. I probably will have the quiz for chapter 35, and then we'll start chapter 36 on Wednesday, if that's all right with you guys. And then, like I said, I'm going to post a bunch of labs for today, just covering all the linear applications of op amps. And then we go through maybe a hitch. Oh, you know, I had forgotten about that. Yeah, so Brenna, yeah, says we don't have to play with the offset null or anything.
Yeah.
And
all we have is the inverting and the non-inverting inputs, and then the output for the op amp.
Because it also doesn't have the VCC and VEE, does it?
No, not in every circuit. I was looking online to see if there was
the thing. All right.
Else.
I mean, one thing when we go in DC bias these op amps, okay, one, yeah, we have to use the offset null for output balance, but I mean, really, all the DC biasing does, like what it does is it sets our upper and lower DC limits, if you will. So like by setting VCC to be like 12 or 15 volts, right? that's setting my upper DC, and then by VEE being, again, a corresponding rate, like -12 or -15, that's setting a lower DC. And I guess if we deal with an ideal model, and I think they have this modeled after the 741, yeah, you know what? I'm gonna have to go through. All right. I'll have to make sure I go through that there's no anything calling out for that. And we'll just have to basically look at it as always dealing with ideal op amp models. Sorry about that. So yeah, when I post the labs today, I'll make sure I go through them, and then and we'll be dealing with the ideal models always with this thing, which is okay. It just, in some of the cases, it was kind of cool just to, be able to have a full setup. And every time, and then after a while, you just pretty much plugged it all in and looked at your spec sheet and did your offset nulling right off the bat. And then, of course, I probably would have had everybody hang on to their own op amp so you knew what it was every time. See, unlike the transistors, right, with the varying beta, with the op amp, we always have to deal with the offset null. But yeah, I guess in the ideal world, you don't have to worry about that. It's always got the null. But all right, yeah, I'll make sure that all the labs are applicable to the ideal model, and you won't have to do anything where it varies. But yeah, with the labs, yeah, I'm gonna leave them open-ended. I was getting too many. Now I am sticking with the homeworks and stuff like that. I mean, I want to stick to a tighter schedule, just because I feel, because of the course of the class, we have to stay up to date with this, right? So yeah, we won't do, I will probably post the chapter 35 quiz sometime today as well. And then we'll take a look at 36. I think we'll look at that. I start looking at that on Wednesday. We'll start looking at like nonlinear or Frenzel's approach to nonlinear. And then after that, we'll be on track, and then we can jump in. Now, I'd like to, well, we'll have to see how this goes, but if we could get through to, excuse me, chapter 40 would be awesome, but I'm not gonna push it. If we could get through, definitely chapters up to chapter 39 would cover a very good scope of everything at this point, is looking at like analog ICs and analog devices, right? Solid state, if you will. Because really that's what we're looking at primarily, right? Compared to like if you were to go into digital worlds, you're looking at all the digital ICs. With this class, we're looking at basically the analog variants, right? Transistors, diodes, op amps, and then different applications with those, even to the point, and then we can hopefully, if we get to chapter 40, then we can play with a 5x5 timer and look at making some clocks and stuff like that. And actually, that thing is, oh my God. I mean, you're learning it from Bob and digital, but there's so many analog applications to that thing. It's quite the versatile little IC. I would definitely like to cover that if we can. It's one of my favorites. But yeah, I'll take a look at the op amp labs and make sure that we're not dealing with anything that's calling out for VCC or VEE or offset nulling. And then, but yeah, I'll post like a series of them, basically all the linear application style ones, like the summer and whatnot. And then we'll basically get through that this week. And then, like I say, we'll do the introduction on Wednesday to nonlinear, at least with the Frenzel, but I'm not going to post any labs. We might post the homework for chapter 36 on Wednesday, but yeah, that's just a different approach. And then of course we have all the corresponding circuits that we'll go through with that. But yeah, that's pretty much it. You guys doing okay with everything, or?
Yeah, it's been pretty good.
Oh.
I think it's just For me, at least, I'm trying to get used to my schedule because it kind of seems, you gotta have to dig for information about when stuff to do.
Oh, you mean as far as like the labs and stuff, or do you mean like with the homeworks and
No,
whatnot?
I'm just saying in general with all my classes combined, they don't really give you a due date. You just kind of have to dig for it.
Well, if you're in Blackboard, when you select your information, like that drop down where your name is,
Yeah.
so on that, there's a calendar option. If you click on that calendar, any due dates that are programmed into any of your assignments will show up. And that's kind of what's been helping me because I'm taking 3 classes and I'm working 30 hours a week. So I rely on that to try and track what needs to get done and when it needs to get done by. So that might help you.
Yeah. I'm in 4 classes right now and I'm working, 10 hours a week too, but not as much as you, obviously, but still working.
Yeah. It takes up a lot of time.
Yeah, no kidding.
A Blackboard or overlap, it does show you what, like in different colors or whatnot for each class, or what, Brenna?
Yeah, so each class is color coded and you can customize the colors as you want. But yeah, if you click on your name, there's a drop down menu, and normally it shows just the individual classes and links to them. But there are icons on the left hand side of that drop down, and like one has the alarm, so that would be like notifications, the check mark for grades, and then the very bottom left hand one shows a calendar, and when you click on that, it gives you a monthly overview, and then it has your assignments and your quizzes. Anything that's been put into Blackboard with a due date is listed there.
Yeah, so me leaving the labs open-ended with no due dates. Oh, shit. Well,
just from your perspective as well as ours, I really think it's best to give us due dates as guidelines to when you expect us to get these things done, because procrastinators procrastinate, I being a lifelong procrastinator. So I would say if 1 week isn't enough for people, maybe 2 weeks is more flexible. So you can either get it done in the week it's assigned, or you have an extra week to try and catch up.
right. Yeah, because I try to make it, well, keep the labs with the tone of the class, right? So like I say, this week's all linear and then next week's non-linear. So the labs are going to reflect that. Yeah. All right.
And at the end of the 8 weeks, you're going to have every single person in this class in their labs degree, Tom. So that's the other thing that you've got to be thinking about.
Yeah. All right. Yeah, that's coming up quick too, isn't it? Oh my God.
Yeah.
All right. So that we'll do that then. I'll post. We'll post due dates, and then. So if you need extensions on the due dates, we know the drill at this point. You just have to email, text me, or whatever is the best way to get a hold of me, and then we'll work it out. But all right, yeah, we'll do that. So I didn't even think about the calendar application and leaving it open like that. But I will make sure that we have that all set up. That'll be easier, I think, for everybody. All right. Everything else is going good for you guys, or?
So far.
Any questions on any of this? Any of it confusing?
I think other than that, that's pretty much it. Just wanted to ask about, due dates, but everyone's pretty much covered that. So
Okay. Breaking in my unemployment and spending it on alcohol. There you go. But wait, are you allowed to still buy the alcohol? Is that considered an essential item at the store?
If it wasn't, people would go crazy.
I was going to say, I've been spending plenty of money at Bearded Owl these last couple months.
Yeah, my wife has too, actually. But, oh no, I saw some of these guys. I had what was it? I had to go to Casey's was it Saturday, I think? And they got, they got it all where section, stand here, and this kind of crap. And some of these people this one guy just walked in, he was ignoring every single line, just boom, 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 coming real close to everybody. And I'm like, that's how you get those crazy videos where that one guy was strangling that girl because she got in his, like in his personal space or something like that. Oh, God. Probably, well, if you have that your unemployment has to be COVID related, I think, in order to qualify for that extra money, right? Wow. And I thought my wife could drink. Aaron, that's a no.
It depends what bottle of bourbon you buy. You can easily spend more than $200 on a bottle of bourbon.
Well, yeah, but I mean, that's like even beyond top shelf. Then I do like, have you guys tried that? Oh God, I can't even believe I'm talking about. But that Jim, like the flavors ones and stuff, because I like that Jim Beam peach is really tasty now. If you like that kind of thing. Peasants. Oh, Johnny Walker. Oh, I don't know. Jim, well, yeah. I do like that Maker's Mark brand is real good. I don't drink it often. We got Blanton's, Jack's single barrel. Yeah. I do like a rye whiskey as well. That's really a smooth. There can't be no such thing as an expensive rye whiskey, though, right? Isn't that almost like a redneck drink?
It's very boutique now.
Is it really?
Yeah.
Huh. Yeah, because when I was growing up, rye whiskey was always like the cheap. In fact, usually most places didn't even keep it on the behind the bar. It was one of the ones that was under the bars. Like, oh, the rye whiskey, yeah, we got that. The label adds, well, yeah, the label does add the price. Yeah, I went, you guys know that one, what is that place? There's that really big liquor store in Peoria out there. It's kind of.
Not Friar Tuck's?
I can't remember the name of that place. God. I don't know. They got like all those like locked glass cabinets and stuff like that with the crazy, really super expensive booze.
Yeah, Friar Tuck's.
Is that Friar Tuck's?
I'm sure Binny's has some too, but I haven't been to the Binny's here in Peoria.
Okay, because years ago I used to do this inventory job, and we went in there. And this was after closing. You're like in the midnight hours doing like inventory in that big giant liquor store. And afterwards, the owner, he had brought out like a couple of those bottles of that stuff that was in the lock cabinets, like $600 bottles and crap. And he's given each of us like a shot to sample. And I was like, oh my God, it was probably the most expensive night of drinking I've ever had where I didn't actually have to pay a dime. What the hell? Unclaimed freight shipping. Oh my God. I got to quit reading that chat. You guys are nuts. Ugh. I don't think, a good thing it doesn't come through on the recordings. I think chat is like all on its own. Yeah. As long as everybody's doing good, it looks like we're going to be, I don't know, the way the Pritzker's talking, we might be in this mess for a while more, huh? And it's kind of nice for me in a way. The stay-at-home thing is definitely saving wear and tear on my car and gas money in a huge way. Crown Royal, oh, ugh. I don't know about Crown Royal. You think May, middle of June? Possibly. We'll have to see how it goes. Canadian Trader. Yeah, I don't know. Like I say, we'll have to see how it all ends up. I do know that, what are we having now? We at the start of May where the mask order for everybody, I guess, going into stores. Is that true what I heard? Yeah, that's what I thought. I don't even know I don't even have a mask yet. Sewing mask. I might have to do, yeah, because I seen online a couple of things. Holy shit. Really? Well, I'm saying, yeah, like the grocery store and whatnot, especially like, because we do a lot of shopping at our IGA over here, and the aisles are literally big enough for like one person. Just wear a gas mask. Yeah. You can buy those Czechoslovakian gas masks for a pretty good price on those survival websites. All right, we'll see you, Ben. Yeah, I'm done. If you guys are done, I mean, I'll chat with you. I don't mind. I get lonely out here. I only see my wife on a daily basis, and I've run out of stuff to talk with her about. No, I'm just kidding. She'll kill me. Good thing she's in the bedroom. Yeah, I know, right? Yeah, well, I'm serious. I mean, I've been like a hermit for what, the last month now. I think the most contact I had was the other day going to Casey's like that, and that felt odd to me somehow. Yeah, I know. Okay, fine. I'll quit chatting everybody up. I know. Well, you're my only. Listen, my other class is my only human contact outside of my family. My sister lives like a mile and a half away. I see her. I see my wife and the dogs, and that's it.
My 4-year-old asked me if I missed my friends from school the other day. So it is nice to see other people.
No, it's right. It's a little weird after a while. I'm worried that if we do this for too long, we'll start getting that. I don't forget what the name of that people phobia disease thing. You know, where you're afraid to go near other people. I can't leave my house. No. Is my light always leaning on the couch? Yes. Yeah, I got really humongous dogs. Anything that's like on a stand or something like that, periodically, every day gets knocked over. They're huge. They're. You guys have ever seen Newfoundland dogs? Yeah. Well, I got like five. Oh yeah, it's quite the herd or pack. Yeah, they're big too. But yeah, I get, so on a daily basis, the water bowl is a swimming pool every day. I got the one girl, she literally runs around the house with wet feet all day long because she can't help herself. And yeah, and anything standing like a lamp or something by itself, yeah, it gets knocked over a lot. Even the TV moves, and it's on a stand and recessed, and the TV even moves from day to day. I got to re-angle it to look at it right and stuff. Yeah, these dogs are, they are really cool dogs, but they are like the bull in a china shop thing, kind of crazy. But if you like big, giant, lovable dogs that literally want to eat everything you're eating at all times of the day, yeah, get these. And I think they're lap puppies too. 140-pound lap puppy. And my sister has, because my wife, my wife breeds them. My sister has one, and every time I go over there, no matter what, at least one point, I was on the recliner the other day, sitting there, and then the next thing you know, floop, and you can't breathe. I'm like, oh. So yes, my light is always leaning on the couch. It needs support. Because the light, well, I go through a lot of light bulbs. I do. Getting that thing knocked and smashed to the ground every time. It's like, all right, let's plug it in and see what doesn't work now. Early 2000s internet forum. Okay, yeah, I'm done. All right, I'm done. But I'll see you guys on Wednesday, and yeah, I'll post all that stuff up today, and I'll keep in mind about the simulator model for the op amp. But yeah, I'll see you guys on Wednesday.
See you, Tom. Thanks.
All right, bye.
Bye.